All right, Chem team, here's the next round of information coming to you on states of matter. And these are actually going to be two graphs or charts that you're going to put directly into your notebook. You're going to draw each one nice and big on its own page. So let's get started here and take a look at the information we have in front of us. And the first one is going to be called a phase diagram. So the way this is going to work out, it's got these three lines coming off of our graph. And we're going to have two variables or two labels for our axes that we're going to put in there. And over here on our y-axis, we are going to label that pressure. And on our x-axis, we're going to label that temperature. So pause for a second, get all this graph drawn and the axes labeled. All right, so what this phase diagram actually does for us is tell us under which conditions we will actually get which phase, solid, liquid, or gas. So we have three general sections on here, and so each section is actually going to be a different state of matter. So the furthest to the left, highest left, is always going to be where you have your solids. So anything that falls under the right conditions for pressure and temperature in this area would be a solid. The one in the middle here, this middle section, would be liquid. And that means the largest section down here towards the right, anything that falls there would be a gas. And so as we change conditions or different variables here within the pressure and the temperature, we can actually get a solid, liquid, or a gas to change between each state or phase. So there's a couple other points we need to actually mark on this chart. The first one is right in the middle where all three of these lines meet. So that spot right there is called your triple point. And what that means is that if you get under the right conditions with the pressure and temperature, so if we were to actually go and get the pressure and temperature exactly right, we can get all three states of matter, solid, liquid, and gas, to be present and exist at the same time. Also, sometimes you will see over here at the end between our liquid and a gas, you will see what's called the critical point. And after that point is when we're not able to actually be stable enough. We have too much energy or pressure added to it, so we're no longer going to be stable enough, and it's not going to hold together in the normal circumstances that it would between a solid, liquid, and a gas. Okay, and then the last part we need to actually go through and remember about these charts is that each one of these lines between these states represents an equilibrium between the states, or a phase change. So that means if we are right on the line itself, so if we were actually to label that line, that's an equilibrium between a solid and a liquid. So depending on what you did, if you were to move from a solid to a liquid, you would be melting. So if you increase the temperature, it would melt. Or if you went from a liquid to a solid, that would be freezing. So if you look right on any one of these lines, that is an equilibrium. So that equilibrium means that's where it's changing back and forth between the states. So that's an equilibrium between the states. So those are the basics you need to know for a phase diagram. All right, moving on to the next page. This graph is called a heating curve. So again, pause and give yourself a second to get the graph drawn out. So make sure your graph is nice and big and that it is neatly done so that we can label it accurately. And so this is called a heating curve, which means it does exactly what it sounds like. This shows us what's happening to the temperature of a substance as it's being heated from a solid all the way up to when it turns into a gas. So this is an example. If you were to take a solid and start adding energy to it, what happens over time to the temperature? And it's going to have very distinct segments in it. So all substances will look very similar to this in their graph. Now the temperatures will change and the length of time that they are in between each state might change, but in general, the graph, all heating curves look very similar. Okay, and they're always going to start with the lower left being where you have a solid. So section A to B is a solid. Okay, and section C to D is a liquid. Segment E to F is a gas. Okay, so in each one of these where we have our segment has a positive or increasing positive slope, or it looks like it's increasing in value, that is where we only have one state of matter being heated. So from A to B, it's just a solid piece that's being warmed up. Now you notice in between each of our phases, we have a flat area or a plateau where our slope is 0. This is our area where we have a phase change. So if you remember from the other night, we said that whenever we go through a phase change, something is constant. So that something is our temperature. So between B and C, we're going through a phase change. Between D and E, we're going through a phase change. And both of those, our temperature is constant. So that tells us at that point our energy is not going into actually heating our substance, but the energy that we get from increasing our temperature is going into separating the molecules or atoms apart so that they can turn into a liquid or gas. So what we have here is, if we're looking at segment between B and C, is that we actually are turning from a solid to a liquid. So that means that this right here would be considered our melting point. So if we were to follow that flat line over and mark it off, that temperature right there would be the melting point of our substance. So we have two states of matter that are present. So this substance will continually melt until all of it turns into a liquid. At that point, the temperature will rise again. And if we jump up and look at our next flat line or plateau area where our slope is 0, between segment D and E, there we are turning from a liquid to a gas. So here we're actually vaporizing the substance. But we don't have what's called a vaporizing point. So if we actually follow this one over and mark it on our temperature, this would be our boiling point. So at this spot, we would have a boiling liquid where we are turning a liquid into a gas, and it would continue to stay at this temperature until all of the substance turned into a gas, and then the temperature would rise. Okay, so those are the key factors we have to make sure that we label there. So we know that between B and C, we're heating, so this is melting. And between D and E, we're also heating, so that's vaporization. So we have two phase changes. During a phase change, there are two states of matter present, and temperature is constant. All right, now with a heating curve, they could also flip this around and give you a cooling curve. So if you saw a cooling curve, it's exactly the same, except for it's like a mirror image. So it's going to start up, still have a plateau between a liquid and a gas, go back down, have another plateau between a solid and a liquid. So it's pretty much the exact opposite. Your labels are still the same, so that means as you go through, your gas is up here, your liquid is still in the middle, and you end up at a solid. So now instead of this being your vaporizing or boiling point, what you end up getting here, this is your condensing point because you're turning from a gas to a liquid. So if we switch it around, all we're doing now is we're just changing what we're doing with the energy. So we're going from a gas to a liquid. We're becoming more organized or slowing our particles down. Whereas we go down to the next one, instead of being our melting point, we're now turning from a liquid to a solid. This actually becomes our freezing point because now we're freezing. So you can flip the graph around. It's essentially the same, it's just the mirror image. You need to pay attention to how many states of matter are present in each segment and what is happening to the temperature. Bring questions to class. Good luck.